In the previous video, we showed that angle side, AAS, is one of the theorems that works to verify that two triangles are congruent to each other. The first thing we'll do in this video is to show that SSA, side-side angle, does not always work to prove that two triangles are congruent. We'll prove that by example here. So we draw a right triangle, ABC. Let's see, B is the right angle. And now we're going to draw the point X such that it's between the points A and C, so it's somewhere on this line. And the length of BX is the same as the length of BC. So really all you have to do is make an isosceles triangle like this, out of the side BX and BC, those two sides being the same length. All right, so go ahead and put a notch there and a notch there. Now, what do we have? The question here is, which two triangles in this picture satisfy side-side angle? Well, this side is the same as this side in length, and if they both use this side, and then they both share this angle, that means we have two triangles that satisfy side-side angle, SSA, but they are certainly not equivalent to each other. We have triangle ABC and triangle ABX. So that's the answer to this question here. They satisfy that they have the same angle. Well, let's see, let's start with the side. They have this side, they're different sides, but they have the same length. And then they have this side, second side, and this angle. So they satisfy side-side angle, but they are definitely not congruent to each other. Well, now let's see some requirements we can add, or something we can learn about two triangles that satisfy side-side angle. Number 3, let triangles ABC and triangle DEF with the usual correspondence, points ABC corresponding to DEF respectively, be given, and suppose that angle A is congruent to angle D. So we're going to draw another triangle here, and we're going to start it off similar. Basically, we're going to draw a triangle that looks like this. So I'm going to draw that. Instead of AB, that's going to become DE. And then instead of this, I'm going to draw this side, like that. So that's going to be my DEF. So they certainly have this angle in common. Angle D and angle A are congruent. AB is congruent to DE, so put a notch there. And then BC is congruent to this one. It's kind of like we already had up here. So what is this saying? It's saying if they are not congruent, then it must be that the measure of angle C plus the measure of angle F, I'll call that a 2 and call that one a 3 notch. The sum of these two angles is 180. It's very simple to see if you look in the previous picture where this angle, I'll put it with 3 notches, and this angle, these two angles are the same because this is an isosceles triangle. And then how does this angle compare to this one right here? These two are linear angles, so they sum to 180. Okay, so that's what we have here. This angle and this angle, or this angle and this angle, these two, add up to 180, which is these two angles right here. So that's what we conclude. If they are not congruent, then the sum of this angle and this angle would be 180. So a nice fact is, if both of these triangles are acute, which means they have no angle of 90 degrees or greater, this one had 90-degree angle. If it doesn't have any angles of 90 degrees or greater, then SSA works. So another statement we could have made is, let two triangles be acute triangles, then SSA works. Now let's go to some special cases of right triangles. So the first one on right triangles, we'll call it corollary HL, which stands for hypotenuse leg. Now remember, right triangles, if you have two of them, they always have one angle in common. That's the right angle, the 90-degree angle. So this says, let triangles ABC and DEF be given and have the usual correspondence. And we're saying here that the measure of angle B and the measure of angle E are both 90 degrees. So I've drawn that right here. B and E are both right angles. And let's see, we have AB congruent to DE. Notice that's not the hypotenuse. And also AC is congruent to DF, which is the hypotenuse. Okay, so if we have that situation, then we have two congruent triangles. Triangle ABC is indeed congruent to triangle DEF. And notice this is kind of a special case of side-side angle, because we have the hypotenuse, that's one side, and then this side, and then we have an angle. So in right triangles, if we have the hypotenuse and then a side and then the right angle, that means we have two congruent triangles. Again, that's HL. Now we're going to move on to HA, which means hypotenuse angle. So we've got some pictures I'm going to have to fill in here to finish these drawings. They're going to look very much like this, but hypotenuse angle. We have two triangles with the usual correspondence. We have the measure of angle B and the measure of angle E. They're both 90 degrees. If the measure of angle C is the same as equal to the measure of angle F, we have this situation. And AC, the hypotenuse, is the same as DF. So we need to extend this to make a triangle. And we end up with this and that being congruent. AC congruent to DF. Then the triangles are congruent. So if we put the point A there, put the point D there, if you just connect them, the triangles are congruent. So we had the hypotenuse and another angle. The length of the hypotenuse, and then the angle C and the angle F. Hypotenuse angle is all you need. The reason being, we actually have two angles because they're right triangles. We have two angles and the hypotenuse being the same. So that means that triangle ABC is congruent to triangle DEF.